College Algebra, Module 2, Topic 2.1, Functions and their Representations. In order to take a module quiz in this class, you must show a completed study guide for each video that you watch. If you have not printed off a study guide for Module 2, Topic 2.1, please do so now. Once you have your study guide, please follow along with the video, taking notes as you go. If you have any questions, please let us know. Intro to Functions. Suppose you got a job in the campus cafeteria and you will earn $8 an hour. In addition to this, you will receive a $10 bonus each week since you are a student. Think about how much money you could earn each week. If you worked 1 hour, then you would earn $10 for your bonus and $8 for the 1 hour, which would be $18 for that hour. If you worked 2 hours, then you would still get your $10 bonus, but you would get $8 times 2 hours, which would be 10 plus 16, so you would get $26 for working 2 hours. If you worked in hours, this is any number of hours, you still get your $10 bonus, but then you get $8 times the number of hours that you work. This is how functions work. A function is a relation in which each element in the domain corresponds to exactly one element in the range. If we let x represent the domain and y represent the range, then for every x value there must be one and only one y value. We may represent functions with words. We may represent them numerically with a table. We may represent them graphically with a graph, or by diagrams called mappings, or symbolically with a formula. A relation, if you'll remember from the last module, is any set of ordered pairs. A function is a special type of a relation in which every x value has one and only one y value. If we denote the ordered pairs in the relation by x, y, then the set of all x values is called the domain, and the set of y values is called the range. This is exactly what we did in Module 1. A function is a relation in which each element in the domain corresponds to exactly one element in the range. The x values, the domain, are called the independent variables. They can be whatever they choose to be. The y values, which would be the range, these are called the dependent variables because they depend on the value of x. Find the domain and the range of the relation 7, 3, 11, 8, 10, 1, and 10, 6. The domain, if you'll remember from last module, was 7, 11, and 10. The range, or the y values, is 3, 8, 1, and 6. Does this also represent a function? If every x value goes to one and only one y value, then it's a function. 7 only goes to 3. 11 only goes to 8. But you notice here how we have 10 paired with 1 and then 10 paired with 6 again? That means no, this is not a function because the x value 10 had two different y values. Objective 2, evaluating functions. To evaluate a function for a particular input x means to find the corresponding output, or y. For example, if f of x equals x minus 2, f of x is just function notation, meaning the formula is called f and the variable is x. F of 3 means evaluate this function's value when you replace the x value with the 3. So f of 3 would be 3 minus 2, which is 1. F of negative 5 means everywhere you had an x, plug in negative 5. So we get negative 5 minus 2, which would be negative 7. F of k means go into the formula. Everywhere you had an x, plug in k. So in this case, it would be k minus 2. This time, let's do f of x as x squared minus 3x plus 1. To find f of 2, we go into our f function. Everywhere we had an x, we plug in 2. So that would be 2 squared minus 3 times 2 plus 1. Simplifying this using the order of operations, we get 4 minus 6 plus 1, which would be negative 2 plus 1. So f of 2 is negative 1. Now let's find f of negative 1. Now it's always a little tricky when you've got negative numbers in exponents. So we've got negative 1 squared minus 3 times negative 1 plus 1. Now remember, for this one, negative 1 squared means negative 1 times negative 1, which is a positive 1. If you put that in your calculator, make sure you put the parentheses around the negative 1. Then we have a minus 3 times negative 1, which would be negative 3, plus 1. So this becomes 1 plus 3, which is 4. So 4 plus 1 is 5. So f of negative 1 is equal to 5. Let's try another one. If f of x is 4 over 3 minus 2x, find f of 2 and f of a minus 1. Well, f of 2 is exactly what we've been doing. Go into the function. Everywhere we had an x, plug in 2. So we get 4 over 3 minus 4, which would be 4 over negative 1. So f of 2 is negative 4. F of a minus 1 means go into your f function. Everywhere you had an x, plug in a minus 1. So we get 4 over 3 minus 2 times a minus 1. Now to simplify the denominator here, we're going to distribute the negative 2. So we get 3 minus 2a plus 2. Combining like terms, we get 5 minus 2a in the denominator. So f of a minus 1 is 4 over 5 minus 2a. Objective 3, graphing functions. If f of a is equal to b, then the point AB lies on the graph of f. Likewise, if AB lies on the graph, then f of a is equal to b. The whole point of this is like your x value, and the y value is like your f of x value. We can graph functions several ways. We can graph them by hand by plotting points. We can graph them by function recognition, which we will do later, or we can graph them with a graphing calculator. To graph a function by hand, since a function is a relation, which is a set of ordered pairs, we can graph the function by plotting the ordered pairs. Of course, for most functions, it is impossible to plot all the ordered pairs, so we plot several points and connect them with a line or a curve. Let's graph f of x equals x minus 2. To graph this, we're going to need some ordered pairs, so let's just pick some points. Let's let x be 0, let's let x be 2, and let's let x be negative 2. If we let x be 0, then f of 0 is 0 minus 2, which is negative 2. If we let x be 2, then f of 2 is 2 minus 2, which is 0. So f of 2 is 0, which means if x is 2, the y value is 0. Same thing for f of negative 2. We would get negative 2 minus 2, which is negative 4. So we get negative 4 for the y value. Now 3 points is probably enough. Sometimes we'll need a few more, but for these I think 3 will work. So now let's graph these ordered pairs. For the first one, if x is 0, y is negative 2, is over 0, down 2. The second ordered pair, 2, 0, if x is 2, y is 0. And then the third ordered pair, if x is negative 2, y is negative 4, back 2, down 4. So there are our 3 points. Then we want to go through and draw a line that connects all 3 points. So this function, f of x equals x minus 2, is a straight line through those ordered pairs. The next example, f of x equals x squared plus 4. We're going to start by plotting some points. So if we set up our table, x and f of x, so if x is 0, we would get 0 squared plus 4, which is 4. Let's do another one. Let's choose 2 again. If we choose 2, f of 2 is 2 squared plus 4, which would give us 4 plus 4, which is 8. We'll just go back and do negative 2 again. So f of negative 2 means negative 2 squared plus 4, which again is 4 plus 4, which is 8. Now we're ready to plot those points. If x is 0, f of x, or the y, would be 4. So that is over 0, up 4. The next ordered pair, 2, 8, is over 2, up 8, which would be right here. And then the third ordered pair, negative 2, 8, would be back 2, up 8. Now notice this one is not a straight line. This is actually what we call a parabola, which looks like this UV thing, and we're going to talk about those later on. Graphing with a calculator. If you enter a function into the graphing calculator, the calculator can make a table of values and draw the graph of the function. This is a great way to check that you have not made any errors while graphing by hand. So to graph the function f of x equals x squared minus 3, something you need to check after we've been plotting our scatter plots and our line graphs is when you go up to y equals, you see how the plot 1 is highlighted? That's going to give you an error when you start to graph. So always make sure you go up to plot 1, press enter to unselect it. Now you'll be ready to graph. So for this function, we're going to enter f of x just like we would y equals. We're going to go x to the second power minus 3. After entering x squared minus 3, because we forgot to set our window to the correct size, we can go ahead now and go zoom 6 for standard, and there is our graph for x squared minus 3. If we're looking to see exactly which points we needed on this graph, we can go second table, which is second graph. That will allow us to arrow up and down. This tells us when we plugged in 0, we would get a y value of negative 3. Or if we plugged in 1, we would get a y value of negative 2. So to graph this on our paper, we're going to draw our x-axis and our y-axis. We're going to come over to see on our graph where x is 0, y is negative 3. We're going to put that one on there. If x is 1, y is negative 2. We can put that one on there. If x is 2, y is 1. Notice we need some more on the other side because that graph, it looks like it might go down like that, but it does not. So if x is negative 1, y is negative 2. And if x is negative 2, y is 1. So we would copy this graph over onto our paper. Okay, let's do another one. Then when we press graph, that gives us the graph that looks like that. To graph it on paper though, you really need some points, so we can go back to second table and copy some of those points over. If x is negative 1, y is negative 10. If x is 0, y is negative 5. If x is 1, y is negative 2. If x is 2, y is negative 1. If x is 3, y is negative 2. We could arrow down to get a few more points. If x is 4, y is negative 5. You see the pattern now? It's just going to start going back the same direction on the other side. So that's how we use our calculator to graph functions. Objective 4 is domain and range. The domain is the set of all possible x values that give a real number y value. As a rule, we cannot use x values that make the denominator of a fraction 0. We cannot use x values that make a negative value under a square root symbol. We also cannot use x values that do not make sense in an application. It is possible to find both the domain and the range of a function once it has been graphed. For example, look at this graph and find the domain and the range. You see, the domain are any x values that have a point represented. So this point would represent this x value. This point would represent this x value. So basically, everywhere there's a graph, that's what's shaded on the x value. Because that goes all the way to the right, that would include all x's over here. Because this one goes all the way to the left, so our domain is going to be the entire x-axis, so the domain would be all real numbers. The range, on the other hand, is the y values. You notice this y value starts right here at negative 10. There's y values all the way up on your graph, then the range is also going to extend forever. So the range would be all real numbers greater than or equal to negative 10. Another way to write that is to just say that y is greater than or equal to negative 10. So for this problem, find the domain and the range. The domain is the set of all x values that have a y value on the graph. So your domain would be the set of all numbers less than or equal to 4. The range would be the y values that are present on the graph. The range would be from this y value at 0 all the way up, because eventually that y value, that graph, is going to go all the way up. So on our paper we would say that the domain is all x's less than or equal to 4, and then the range is all y values greater than or equal to 0. Okay, we'll start with the domain. The domain are the x values on the graph, so we have an x value starting here at negative 3, and we have x values all the way up to 3. If you'll think about it, just drop every point on these graphs to the x-axis, and that gives where the x values should be shaded. The range is the set of y values on the graph, so our lowest y value is negative 6, our highest y value is 6. We have y values all the way between negative 6 and 6, so the range would be all y values between negative 6 and 6. So the domain, going from negative 3 to 3, we would write x is greater than or equal to negative 3, but less than or equal to positive 3. And the range would be all y's between negative 6 and 6. So we're going to write that as y greater than or equal to negative 6, but less than or equal to positive 6. So how do we find the domain if we don't have a graph? Well, one way would be to look at the graph and then pick the domain from there. The other thing to look at is if there are no fractions and no square roots, then the domain is going to be all real numbers. Now we have a fraction, f of x equals 1 over 3x plus 2, and we have to be concerned that the denominator is not 0. So what we do is we find what makes 3x plus 2 equal to 0. Well, to solve that, we're going to subtract 2 from both sides. We get 3x equals negative 2. Divide by 3, and we get x would be negative 2/3. Now remember, that's the value that makes the denominator 0. So our domain is going to be all x's except negative 2 over 3. And then our third part says if f of x equals the square root of 3x plus 2, what is the domain? Well, remember when you're taking the square root, you can't take the square root of a negative number, so whatever is under the square root sign can't be negative. So what we want to do is we want to find what makes 3x plus 2 greater than or equal to 0. So we could subtract 2 from both sides, so we get 3x is greater than or equal to negative 2. Dividing both sides by 3 gives us x is greater than or equal to negative 2/3. So that would be our domain for this one. Now let's use the graph of g of x equals 4 minus x squared to complete the following. Find the domain of g. Domain are the x values. Well, if you look on this graph, the x values could range from the left side all the way through to the right side, so the domain would be all real numbers. And sometimes we'll write that sort of with a bolded R. The next part says evaluate g of 0. Well, g of 0 means find the function's value when x is 0. So if x is 0, that ordered pair is right here. So that's the ordered pair actually 0, 0, which means if the x value is 0, the y value is 0, so g of 0 is also 0. And then evaluate g of 4. G of 4 means find the function's value when x is 4. So if x is 4, the function actually hits a nice point right up there. That is the ordered pair 4, 5. So g of 4 would be 5. Okay, so this function notation is pretty much like an ordered pair. The number inside the parentheses is the x value. The function's value is the y value. Objective 5, identifying functions. A function is a relation that states for every x value there is one and only one y value. To determine if a relation is a function, we must make sure that each x value has one and only one y value. This process will vary based on what you are given, either a set of ordered pairs, a formula, a graph, a table, or a diagram. Tell whether this table represents a function or not, and if not, tell why not. Well, all of the x values are different, which means it's going to be a function. There are no repeated x values, therefore we cannot have the same y value. Yes, that one is a function. This one is actually called a linear function because the graph is a straight line. Tell whether this table represents a function or not, and if not, tell why. Well, you notice on this one, we actually have the same x value repeated twice. Well, the first time the x value is negative 2, the y value is 1. The second time the x value is negative 2, the y value is negative 1. Therefore, this one is not a function because the x value negative 2 had two different y values. Now tell whether this table represents a function or not. If not, tell why not. Well, you notice all of the x values are different. Therefore, it's going to be a function. It does not matter that all of the y values are the same. What matters is that every x value can only have one different y value. So this one is a function. And actually, this is what we call a constant function because the y value does not change. For this example, tell whether s is a function or not, and if not, tell why not. This time they give us ordered pairs instead of a table, but when we look at our ordered pairs, we've got negative 11, negative 10, negative 22, negative 12, and positive 11. Because all of the x values are different, then yes, this is a function. This example, looking at the x values, we have 13, 14, 26, 12, and 13. Notice 13 occurred twice. The first time we had a y value of 4, the second time we had a y value of 1. That means this is not a function because every x value did not go to one and only one y value. Now the vertical line test is a test we use to tell if a graph is a function or not. It says if every vertical line intersects a graph in at most one point, then the graph represents a function. That is, if you can draw a vertical line on a graph and not hit that graph more than once, then it's a function. The first one we draw hits our graph in two places. Because it hits it in two places, this one is not a function. What that means is the x value of negative 7.5 had two different y values, which makes it not a function. The next graph, if we drew vertical lines throughout the graph, you notice we only hit the graph in one spot, then it is a function. Now let's look at equations. How would we tell if the equation was a function or not? So doing a little bit of algebra on here, if we subtract x from both sides, we would get negative 3y equals 9 minus x. If we divided both sides by negative 3, then we get y equals 9 minus x divided by negative 3, which means no matter what x we plugged in, if we subtracted it from 9 and divided by negative 3, we would only get one y value. One y value for each x value, that is. So yes, this one is a function. The next one, x plus y squared equals 12. Same thing. Doing a little bit of algebra on here, if we subtract x from both sides, we would get y squared equals 12 minus x. Now remember back when we did square roots, remember there were two possible cases, which means y could be either a positive or negative square root of 12 minus x. So because it's a positive or negative, that makes it more than one y value. Therefore, that is not a function. And your rule is anytime you see a y squared in an equation, it is not going to be a function. This one, y equals the third root of x plus 9, that one is a function because for any x value we plug in there, we are going to get a unique y value. So yes, this one is a function. Objective 6, representations of functions. Recall our introduction. Suppose you got a job in the campus cafeteria and you will earn $8 an hour. In addition to this, you will receive a $10 bonus each week since you are a student. Think about how much money you could earn each week. How would you describe your pay in terms of the number of hours you worked each week? And we talked about that at the beginning. The verbal representation is $10 plus $8 times the number of hours we work. We could also say 10 plus 8 times x, where x is the number of hours that we work. The numerical representation is like a table. We could have a table set up that says if you worked 1 hour, you would get $18. If you worked 2 hours, you would get $26. If you worked 3 hours, you would get 3 times 8 is 24, plus 10 would be $34, and you could do your table like that. Symbolic representation would be 10 plus 8x, and then the graphical representation, we could draw a graph for this, plotting the points we did here. If x is 1, y is 18. If x is 2, y is 26. If x is 3, y is 34. And we would have a linear graph here because this is a linear function. We can also use diagrams or mappings to represent functions. For example, consider showing the possibilities of 3 children choosing either chocolate, strawberry, or vanilla ice cream with a topping of either chocolate or caramel. Well, the domain would be your ice cream. So we would have chocolate, strawberry, or vanilla. So we would usually have a group of domain. The range would be our toppings. So we would either have chocolate or caramel. And then to write them as an ordered pair, if we've got 3 children, they have to pick. Well, maybe this one likes this one. Maybe the chocolate likes the chocolate topping. Maybe the strawberry likes the caramel topping. And maybe the vanilla likes the caramel topping also. So for those 3 children, we would write this as the ordered pair: chocolate, chocolate topping, comma, strawberry with the caramel topping, comma, vanilla with the caramel topping. There's lots of options here, but that's how the mappings work, is you would just show your choices based on the drawings with the arrows. Now, would this particular mapping represent a function? Well, the way we've got it, yes, because each one of the ice creams went to only one of the toppings. However, if we would have changed it and the first child wanted chocolate with chocolate and the second child wanted chocolate with caramel and the third child wanted vanilla with caramel, then this one would not be a function because the chocolate was chose twice with 2 different outcomes. Okay, let's do another. Write a function f that computes the cost of an X mile cab ride for which there is a $2.25 charge for the first mile and a charge of 63 cents per mile for each additional mile. Our function would look like this. F of x equals 0.63x plus 2.25. This is our fixed amount. Everybody's going to have to pay that. This is our variable amount because that will vary based on how many miles you go. Write a function f that computes the time in hours that a car has been on the road if the car is traveling at a rate of 40 miles per hour and has covered a distance of x miles. For this one, you'll probably need to remember that distance is equal to rate times time. So we are trying to write a function that computes the time. Well, if we have d equals rt and we want to get t on a side by itself, then we're going to divide both sides by r. So t is distance over rate. So for our problem, f of x is going to be the time, the distance is x, and the rate is 40 miles per hour. So this is a formula for any number of miles. We should be able to calculate the time that it will take us to go that number of miles. Another application. A train is initially 150 miles from the station and moving towards the station at 20 miles per hour. Write a formula that calculates the distance the train is from the station after x hours. To start with, we want to remember that distance is equal to rate times time. So our train is actually going 20 miles per hour, which is the rate, times the number of hours, which is x. So this is the distance that our train is going. The question asks us to calculate the distance the train is from the station after x hours. So what we've got is our big distance is we started at 150 miles away and then we're moving our 20 times the number of miles after that many hours. The next part says how far is the train from the station after 3 hours? Well, we can just plug it in our formula. That would be d of 3, which is 150 minus 20 times 3, which is 150 minus 60. So after 3 hours, the train should be 90 miles from the station. You are now ready to do the homework for Module 2, Topic 2.1 in my math lab.